Okay, so invert binary tree, flip left and right nodes using recursion, yada yada yada, all the good stuff. Alrighty, let's do this. Hi, welcome back to the channel. So if you're new here, my name is Michael. I'm a computer science student, and I solve coding and Invert questions. So today we're going to invert a binary tree. This is yet another easy question, and it's number 226 on LeetCode. So let's dive right into it. So I'm going to assume that you already know what a binary tree is. If you don't know what it is, I highly recommend you look it up. For those of you who already know what it is, I'm going to give a little bit of background. It's a data structure that each node has two children nodes, a left child node and a right child node, and either of those children nodes could be null at any point. And when you get down to the leaf nodes, all the children nodes are null. So this is an example of a binary tree. And so this question gives you one binary tree, and I'm going to call this I for input, and you should return this flipped version. You should flip the binary tree and return the flipped version of it. I'm just going to call it O for output. And yeah, so if you closely look at the line in the center, it kind of acts like a mirror, and it's reflecting both binary trees. So how do we do this? So if you look closely at the children nodes, I'm going to label them. You could see that the right child node for the root node in the original binary tree is 7, but the left child node in the inverted binary tree is 7. So the right child node becomes the left child node. So you could start to see where we're heading with this, right? So this is the left child node, just going to call it L. So how are we going to solve this? So we're going to do a pre-order traversal on the binary tree, and when we get to every node, we switch the left and right children nodes. I'm just going to label the entire binary tree. So this is the right node, and this is the left node too. For the node with value 2, this is the right node, and this is the left node. For the node with value 7, this is its right node, and this is its left node. And then we get to the other binary tree, and this is for root node 4, this is its right node, and this is its left node already labeled. And when we get to 7, this is the left node, and this is the right. Oh my god, I don't know left from right. Right node, this is the left node, this is the right node, and this is the left node. Awesome. So whenever we get to every node, we flip the left and right children. We swap them. So we swap 2 with 7. So now 7 becomes 2, and 2 becomes 7. And we do that for all the other nodes in the binary tree. So why is it called a pre-order traversal? Well, pre-order traversal says that you visit the node first before visiting its other children nodes. It's like node, left, and right. So you visit the node. After visiting the node, then you pass in its left and right children into the recursive calls. So let's do this. Where is the code? Okay. So we have access to the root node. First of all, I'm just going to do a quick check for an edge case. This is also going to be our base case. So if root is equal to null, then we could just return, what do we have to return? We have to return root. Okay. So if the root is not equal to null, what we could do is we could swap its left and right children nodes. It's going to say swap left and right children. So do I need to declare a helper function to handle the swap operation? I'm pretty sure yes. So I'm just going to declare a helper function, call it public void swap nodes, and this is going to take in the left and right children nodes, or Considering the fact that we already have access to both the left child node and the right child node for every node in the binary tree, there's actually no need to pass in that many parameters. All we could pass in is one parameter, and that's for the root node. And then we could declare another true node, temp, and here we're going to store root.left, and then we're going to set root.left to root.right, and then we're going to set root.right to temp. And this is a classic swap function. Alrighty, so all we have to do now is call swap nodes on the left child and the right child of the current node that we're already on. And so that would be root, and that's it. So going back to the pre-order traversal thing, we do have to pass in the left child node and the right child node into the recursive call. And so I'm just going to call this function again. It's the invert tree. And for this time, it's going to be root.left. And then I'm going to call in the same function, but now I'm going to call it with root.right. But I'm sure we have to check for an edge case where the left node doesn't exist, because there could be times when the left node is null or the right node is null, and we don't want to get to this point and return without checking the right child. So I'm just going to do an if statement here. So we want to make sure if we have a left node, so if root.left is not equal to null, then we could invert yeah, it could work that way. Yep. And we do the same thing for if root.right is not equal to null. And we do this. So I think that is pretty much all we have to do. And at the end of everything, we just want to return the root node. Okay, just going to go through swap the nodes, check if there's a left child. If there's a left child, we pass it to the recursive call. Then when we pass in the left child, then we swap the nodes of the children nodes of that left child, and we pass in the right child, and we swap the nodes, the children nodes of that right child, and that's pretty much it. So I'm just gonna run this. Cool. So submit. I hope it was accepted. Right, and it's faster than all the other submissions for Java. Alrighty, so let's dive into the time and space complexity of this algorithm. Where's my whiteboard? So for time complexity, because we're going through every node in the binary tree, this node go to its left child and its right child, left child, right child, left child, right child. I'm going to say time complexity is O of n. It's O of n. And for space complexity, I'm also going to say it's O of n because of the recursive calls that we're making. And space complexity is O of n. We could also choose to solve this question iteratively, and that's still going to be O of n, because then we'd have to get like a stack or queue to store the nodes and then pop them out of the stack or pull them out of the queue. It's still going to be O of n. So because of every computation has been added to the call stack and the recursive call stack, so that's O of n. So that's it for this video. I hope you find it informative, and I hope you had as much fun watching it as I did making it. And share it around the community with your friends and family who are preparing for their coding interviews, and also comment down below. Let me know if there are ways you think we could have made this algorithm work better. And smash the like button for the YouTube algorithm. And I'll see you in the next one. Bye-bye.